So she's going to talk about the semiconductor ecosystem in India. Okay. So please listen to it, and if you have any doubts, you may ask the doubts, or if you want to have an interaction session with her, you may ask it towards the end of the session. Okay. Thank you. We will start.
Thank you, sir. Once again, good afternoon to all. So it is really, I'm humbled and proud to speak about semiconductor ecosystem in India on this occasion of, we have already seen in the morning, Honorable Prime Minister has laid on the foundation for 3 major semiconductor facilities in our country. So with the background of that, I'm going to speak about some of the past of semiconductor system in our country, and then what is currently going on in the ecosystem, and what will be the future prospects as a budding engineer for the students and as an academician, and for the industries also, what will be the future for semiconductor in our country. That is the overall key points that I just want to share with you with this presentation. I also lead a research group in IIIT Kottayam, Intelligent Integrated Circuits and Systems Research Group. This is basically, we do a lot of research in the VLSI domain. We have a couple of PhD scholars, undergraduate students, BTech Electronics and Computer Science students who are working rigorously for various VLSI design aspects, and has published several papers, several quality papers in prestigious journals, conferences over the globe. So I'll talk about the research group a bit later. Moving on to the presentation. This is the agenda. This is the agenda of today's presentation. So we'll discuss about semiconductors. It's a very popular term nowadays, semiconductors, which is going to power the digital revolution. It is already powering the digital revolution. Then what is the current semiconductor market of our country, Indian semiconductor market? Then what are the reasons for? Suddenly we have seen a boom in semiconductors. So what are the reasons, major reasons for such a growth in semiconductor industry? Which are the silicon pioneers of India, from the country of India, who are leading the industry right now. So probably undergraduate students will get a know-how of the different job prospects also from this particular slide probably. Then what are the initiatives from our government? Government of India has a lot of initiatives right now for supporting semiconductor ecosystem in the country. So we will just see what are them from academic perspective and from industry perspective also. Then what are the latest updates and opportunities and the future of semiconductor? This is the overview of today's presentation. So coming to semiconductors, okay, if we have 5 people in a room, we will be having more than 5 electronic devices in the room. Probably we will be having 10, 20, 30, 40, etc. Even if you are a single person in a room, you will be having at least 10 plus electronic devices in that particular room. So semiconductors are powering the digital revolution. That's why semiconductors are powering the digital revolution. It is a building block of all modern electronic devices. And the history of semiconductor, it started from 1960s onwards in our country, when government of India has established the first semiconductor complex in Bangalore. Then later, after 2 decades or so, India became major exporter for semiconductors. So, and now we have a huge boom in semiconductors. So why is that so? So we will see that in the next few slides. So this is the graph where we stand. Where is Indian semiconductor market currently standing? So you can see in the second diagram, you can see in 2021. So Indian semiconductor market, out of the total global market, we are in 9% of total market share. Then it has raised within within 2-3 years or 4 years, it has raised it has doubled. Basically, it has doubled, and this graphs, and this measures this quantity or these measures have been taken from we have an association for electronics, that is Indian Electronic Semiconductor Association, and then we have VLSI Society of India, who are providing so many such market reports which are useful to see where we stand right now. And, going back to the design flow, or not design flow, starting from the raw material, what is the semiconductor value chain? That's what we are seeing in the slides. Starting from raw material collection, you have the device on your hand. This is the entire process starting from 1 to 9. So raw material collection, then you have capital equipment as wafer foundry, then manufacturing equipments. So those are capital equipments starting from material collection. Then you go for IPs and EDAs. So this is where the design, IP and EDA and design. Coming to narrowing the semiconductor value chain, you have design also there. So once you come up with the particular functionality, you make a design of that particular functionality, then you can give the specifications of that. Probably it's a multiplier or it's a convolution unit, whatever may be. So you give the specifications of that. Okay, this multiplier, this optimized multiplier which I have done, maybe RTL coding synthesis, everything I have done, I am going to make it as an IP, intellectual property. So you can give a specification. This multiplier can work for an operating frequency of 500 megahertz. Is the maximum operating frequency that I can have. So that is a major focus. It was the major focus till now, IP and EDA and design. So design means again coming to the processor designs, microprocessor designs, or whatever, building blocks from modules you develop processors, etc. So till this time we were discussing about, almost all the companies were discussing or focusing on designs, and now the situation has changed. We have moved on to the fabrication also. That's what we have seen in the morning also. Fabrication fab facilities have been launched in the country. So there comes the back end product, PCB end product, etc. It comes in the fabrication side. So we have moved to that level right now. So why this semiconductor has a huge boom these days? It's because you have a lot of demand for gadgets, but this chip designing is a time-consuming process. Supply does not meet with the demand. So there is an opportunity for industries to grow there. Potential growth of semiconductor industries can happen, or growth in the chip design industry can happen, because you have a lot of demand for gadgets, electronic equipments, especially during COVID and all. Supply was very less for ICs. So this may be one of the reasons that has created a huge growth in the semiconductor industry or domain these days. Unprecedented growth in domestic consumption of electronic goods. So which are the key actors in India's semiconductor ecosystem? So this is just I have taken this, I have given the courtesy in some other slides probably. So this is just an overview. It's just for this is the first step is pre-competitive research. Before you go to design, you will have to do some kind of research which happens in academic side and in research organizations. So it's just for visualizing it. We have shown here Center for Nanoscience and Engineering, Science, DRDO, IITs, etc. So everywhere in almost all the academic institutions where VLSI has dominance, a big quality research is happening there. The next stage is design. So we have certain companies which have design centers in India, Intel, Micron, Qualcomm, AMD, and now Micron has moved to fabrication also in India. Qualcomm, AMD, Marvell, ST. So many companies are there. Apart from this, we have a few more in the list. Sankhya Labs, Signal Chips, Teridian, Cyril, etc. So those are fabulous. So India, government of India also has an initiative. They have government has an initiative which support fabulous laboratory, which supports industries, and that can be incubated into a fabulous laboratory. So we will speak about that in one of the slides. So these are some of the companies which focus on designs. So far it was design. Now in India, design in India basically. The next, coming to manufacturing side. So we have Semiconductor Complex Limited, SCL in Chandigarh. Then Sitar, so many are there. Then coming to packaging, you have SCL, Micron, Tessol. Then coming to MEMS and discrete components, you have Bell, Sitar, etc. So this is from a very it's very it's not a big list. It's not a big list shown here. Coming to equipments, so now you have IC manufacturing units, and SCL basically supports for almost for all the academic purposes we used to send to SCL 180. They support 180 nanometer ICs. And coming to equipment, so apart from this IC designs, we need equipments also for performing all this manufacturing, etc. So which are the companies that support equipments? So you have Applied Materials, Lam Research. Lam Research has recently launched a unit here. It's a US based company. They have recently launched a unit, Lam Research India, in collaboration with Center for Nanoscience, IISc. So these are some of the companies for equipments. Then coming to EDA tools, obviously these are very popular EDA tools vendors, EDA tool vendors, Synopsys, Mentor, Cadence. Just to give you a broad overview of where the companies are, which are the companies which support design, manufacturing, tools, etc., EDAs, etc. Now coming to some other pioneers of India. So the list is very small here in this particular slide. So we have more numbers now. This is just for your understanding that Micron, AMD, NXP, all these are silicon pioneers. Then you have some more ChipLogic, Sankalp, Cedil, NVIDIA, etc., Qualcomm, Tata, Sankhya Labs, etc. So some of these companies are described in some other slides also. Some companies are startups. We will see that. Coming to semiconductor R&D and design, of course, IC design is undoubtedly India's greatest semiconductor industry strength. So out of total strength in the world, India accounts for about 20% of semiconductor design engineers. And every year we design 3,000, approximately 3,000 ICs, individual ICs. So this is just to show the strength of VLSI design in India. In coming to VLSI, obviously VLSI means you are cramming more and more transistors onto the chip. So India accounts for 15% of the global production in VLSI systems, VLSI chips. And almost world's top 25 semiconductor design companies have their centers in India, R&D centers in India. Intel, almost big giants, Intel, TI, NVIDIA, Qualcomm, everybody is having R&D centers in India, and they are located in the central in the city of Bangalore, southern city. This is about the R&D and design. And coming to some companies. First company to set up R&D center in India is TI, in Bangalore in 1985, and then later on came many R&D centers. For example, Synopsys has an R&D center. So now, chip to startup program is running. You may be knowing that. So Synopsys tools are available through C2S schemes. Then we have AMD. AMD has a design center. Then Samsung was already having, but recently they have inaugurated the Samsung Semiconductor India Research. Then many of these companies, they are basically design based in India, design based industries in India. So we call them as fabulous. They are fabulous. They do not have production in India, but Instead, they'll outsource this to foundries like TSMC, Taiwan Semiconductors, or global foundries. And beyond this IC design, yes, we have manufacturing also. So that's what I was telling in the previous slide. Lam Research Corporation, so you see manufacturer, they have launched Lam Research India in collaboration with Sense. This is about the semiconductor R&D design. Now coming to startups, again, government of India has a lot of initiatives for supporting startups in India. So some of the startups are mentioned here. MindGroove Technologies, so Chennai-based startup. They are designing 28 nanometer chips for devices like automobiles, for connected devices basically. Then Inco Semiconductors, it is very popular these days because of the revolution in RISC-V processors. Then you have Sankhya Labs and Signal Chips. So both of them are focusing on communication chips. Sankhya Labs, established in 2006, it is the first fabless semiconductor solution in India. And they are producing software-defined radio chipsets. And again, Signal Chip is also based on wireless communication standards, 4G, 5G chips. And some more startups are here, listed here. You can explore more on that later. And now, which are the different initiatives from the government of India? So initiatives like Make in India, Digital India, Startup India, all these are focusing on to ESDM sector, Electronic System Design and Manufacturing System. And then we had already talked a lot about national policy on electronics. So it promotes electronic components manufacturing ecosystem. And right now in the morning we have seen that also. And then there's another scheme called Production Linked Incentive, PLI schemes. So this is again to facilitate the manufacturing in India, semiconductor manufacturing, IC manufacturing, packaging in India, production linked incentive scheme. So these are some of the major initiatives from the government. And apart from this, yes, we have India Semiconductor Mission. India Semiconductor Mission focuses on semiconductor fabs, as well as display, LED display fabs, etc. Then compound semiconductors, and another initiative is design linked incentive in India Semiconductor Mission. So design linked incentive, recently they have, DLI have supported a few startups, and possibly, I am not sure, for 5 years or so they will give the support until it becomes independent. Some clauses are there. Then next, Semicon India. So Semicon India boom also we have seen for the past 2 years. Semicon India 2022 happened in Bangalore. It was in a very big scale. Semicon India has been conducted. In Semicon India 2023 has also been conducted in a very big scale in Gujarat. And in between there were many symposiums, future designs, meetups. So many meetups were happening as a part of India Semiconductor Mission. And earlier I have said that, okay, there is something called fabless designs. So again, Government of India has another initiative called the SFAL, Semiconductor Fabless Accelerator Lab. SFAL, so companies which are design oriented will be incubated by SFAL, and they will provide access to EDA tools or FPGAs, etc. Then incubation period is few months is the incubation period. Then they provide assistance for all kind of business activities. So SFAL, a lot of companies are associated with SFAL also right now. And then another scheme is SPECS, Scheme for Promotion of Manufacturing of Electronic Components and Semiconductors. Again, this is a focus on value chain, semiconductor value chain facilitation, like display. As I said, in the ISM we have seen display units, display fabs, semiconductor fabs, then testing manufacturing units, etc. And CDAC is the nodal agency that implements the DLI scheme that we have seen in the previous slide. And there is already an initiative called CHIP-in is there, that also you may be knowing, where the tag itself is EDA tools for all to make available. So the main challenge that we see in semiconductor from academic point of view, it is the availability of EDA tools. At least from academic point of view, you can say that it's availability of EDA tools, because these EDA tools are very costly, and you may get one unit, maybe some very small number of licenses you will get within a single unit. And it's since it is very costly, you cannot run a class or a lab for 30-40 students at a time. It's not possible. So EDA tools are very costly. So CHIP-in CDAC has already taken the initiative of giving EDA tools for all. That is also there. And right now CTO's CHIP to Startup scheme, they have supported more than 100 of institutions for with all these EDA tools worth crores, 2 crores or so. So that was a great initiative from Government of India, mighty. And coming to the latest updates, so why this event is being conducted today? Because India has gone to the semiconductor journey of India got a big or a giant leap today by launching. Already Government of India has approved 3 projects for semiconductor fab and outsource assembly and testing facilities worth 76k crores. So how it is getting benefited? Direct jobs for more than 20,000 direct jobs are available. So the first scheme is so the first facility is Tata Electronics Private Limited. So we have seen that in the morning. So semiconductor fab with 50,000 wafer starts per month. So the number 50,000 wafer starts per month, the number itself is scaling is very high for the fabrication. The facilities are very we are looking forward to see the facilities soon. The next approval has gone for semiconductor, Tata Semiconductor Assembly and Test Private Limited. So capacity is 48 million dies per day in Assam, and then CG Power and Industrial Solutions, again with the capacity of 15 million dies per day in Gujarat. So these are the 3 major milestones happened, and we are looking forward to use the facilities of facilities which has been launched today. And these are the latest updates and opportunities. Now, apart from this, from the academia side, okay, IIITT has already introduced courses, various courses in semiconductor. And as you know, that BTech in VLSI itself has been launched by IIITT. It's not like BTech in EC with specialization in VLSI. It's like BTech in VLSI design is already launched by IIITT, which is a great initiative for the academic community. So several courses such as VLSI designing, IC integrated chip designing, semiconductor management, silicon chemical instruction. So many courses have been introduced. And it is seen that government aims to set up soon a Paris Semiconductor Research Center also in this year. These are some of the mind-blowing announcements from the government. So now coming to the future is, of course, future is exciting for VLSI enthusiasts and those who have good involvement in semiconductor industry. With this initiatives, is sure that Indian semiconductor industry will become a major part of the economic growth in India. And from our institute, the institute which I represent, IIIT Kottayam, we have a research lab for VLSI, I2CS research lab, integrated circuits and systems research lab, where we do ASIC design and FPGA based system design are the major focus for us. We have a couple of PhD students working in the area of hardware accelerators and FPGA based system design for artificial intelligence applications of various AI applications are being run on the hardware. So the hardware that we focus is FPGA. And apart from this, we do IP designs also in the area of we have a few IPs also for FFTs, phosphorate transform, and some DSP building blocks. For DSP blocks also, we have some IPs. And a few students currently work on RISC-V based projects also. RISC-V is open source. They are doing security for RISC-V and security aspects also. A few students are working on homomorphic encryption, etc. For machine learning and based on a RISC-V platform and building co-processors for a RISC-V platform. These are some of the works that have been carrying out in our research lab. So with this, so now it's open for discussion. We can have a discussion. If you have any questions, we can discuss that.
Thank you, ma'am, for the enlightening talk. It was good to hear from a professor like you about the state of the industry and what you think the potential and the advancements lie for it. I'll open the floor for discussions. Any volunteers who want to take questions? Any questions?
Hello, ma'am.
Yes, yes, please.
I just wanted to ask what interested you in this subject? What was the main motivation?
Okay. So your question is, how did I get interest in VLSI? Is that?
Yeah.
So I have completed my. Am I audible?
Yes, ma'am.
So I have graduated in 2006 from Kerala. My undergraduate was completed in 2006 in Kerala, and soon after graduation, yes, I was placed in IT company and Technopark. I went there for some time, and then my passion was teaching. Basically, my passion was teaching. So I wanted to do post graduation. Then if you want to go as a teacher, yes, in an engineering institute, you have to do a master's at that time. Yes, of course, in 2006. So I went for. I have then you have to write examinations for getting a PG admissions. Yes. Then in Kerala, there were only a few engineering colleges, who were having a master's degree at that time in 2006. There were only handful of engineering colleges in the state which has a PG. So at that time, yes, we have heard about masters in signal processing. That was very very popular at that time. Masters in signal processing, masters in microwave was also there at that time in Kerala. Masters in then masters in digital electronics. These were the three courses which are popular at that time. in my state. Then then I have heard from some of my friends that there is some course called, we have already done a course as an elective, we have done a course in VLSI during undergraduate. At that time, it was an elective course. It was not very popular. It was not very popular at that time when I was doing undergraduate degree. Then I have heard that, okay, some states in are giving a master's in VLSI. I heard from some of my friends. Then I thought that, okay, we should go for a some other institutes outside the state, of course, for doing a master's in VLSI. Then I have been to PSG College of Technology, where the VLSI, VLSI domain has been, they were conducting the courses very nicely for VLSI students. And that was the first point where I got an interest to VLSI. Actually, we know that something called VLSI is there. That's how I went to a master's for VLSI. But once you are into the course, then it was really interesting for me. And probably of course, the teachers may have influenced a lot. Of course, maybe that may be the primary reasons why I have gone for research also. My teachers, those who have taken this course for me, have influenced me a lot, and that they gave me an inspiration and a motivation to go for a research. That's how I came, until this point.
Okay, ma'am. Thank you.
Thank you so much.
Yeah.
I think we are done with the questions, but I had a question from my side also. Ma'am, taking the Bharat design and Bharat production of, like, we have been designing chips from a long time, but we have not been a force in the market. Like, we don't have our own chip designs which are trademarked to India, and other people licenses like TSMA or Qualcomm. So do you think India would be in a position to, like, does India benefit from having its own designs and licensing it to others, or would we serve better as a fabricator?
No, we are moving to for that only right now, because we are moving into the direction where today itself our Prime Minister was saying that we will make our own chip, make in India, make in Indian fabricated chips will be made soon and will be available to the devices. That's what. That's why all this all the ecosystem has been made like that, and the initiatives have been made by the government in order to promote, and that's why CTOS has been given to so many institutions to make expertise, to get expertise.
Yes, ma'am. Once again, thank you for your input. It was a very informative session, hearing from a brilliant mind like you. We thank you for taking time from your busy schedule to present to us. And
Thank you, sir.
yes, ma'am.
Actually, it was a short notice that we have to do this function.
Yes, ma'am. Yes, ma'am. I think Anup sir would contact you soon.
Yes. Okay.
Sure.
Okay.
Thank you. It was a pleasure to have you here.
Thank you, sir. Thank you so much.
ब्रेक डाला है, ठीक है. Let's turn our attention to our speaker, Professor Binsu J. Kailath. She is a professor at IIITT Kancheepuram. Ma'am did her BTech in Electronics and Communications Engineering from Calicut University, her Masters from IIT Madras in VLSI Design, her PhD in Ultra Thin Oxide MOS devices from IIT Madras in 2007, which further shows her knowledge and commitment to the field of EC. Ma'am has been attributed in numerous studies and research projects, both privately and government funded. Ma'am's field of interest includes neuromorphic circuits, mixed IC signals, and microelectronics. We are honored to have you to share your knowledge with us today, ma'am.
Thank you. Thank you very much. Yeah. So I hope I am audible as well as the screen is visible. Yeah. So today, because I was told that there are students from both EC and CSC background, the topic that is taken for today's talk is applications of AI ML in VLSI, because we see in our students also the mentality of the students is that whenever we say a project is AI based or ML based or deep learning based, the students would automatically come and choose such projects. So I just, with this talk, I just want to give you a flavor of the applications of different AI ML techniques in VLSI design. So if you see the global market, so this is the, let me take font. Yeah. So the compound annual growth rate is given here. It is 53.93 billion billion in 22, which is expected to grow at a 6% growth rate to 81.09 billion by 29. That means only 5 years from now. And regionally, if you see, always the major stakeholder of the semiconductor industry is North America, then Europe, Asia Pacific, including our country. Now, with today's foundation stone laying ceremony, and maybe within 3 to 4 years, India also will start producing commercial semiconductor chips, by which we will also enter into this pathway of semiconductor manufacturing. The major companies that are in the semiconductor market are these companies listed here. So now if you see any application that you see, everywhere for a hardware system, we know that software alone cannot make a system. Along with the software, you need a hardware. So any application that you see in wired communication, there is a 10% increase. Then broadband usage in some countries, demand for switches and routers are more, especially in a post-COVID scenario. There is a 50% increase there. Then video streaming, during the COVID itself, entire education system was online. So there a 40% increase in the equipment that are used for video streaming was there. Consumer electronics, there is a 10% rise. And during the pandemic, as you all know, the VLSI industry was heavily hit by the shortage of chips across, or even in automobile industry was hit because of that. Now it is getting redeemed and going back to the earlier production level. So the rise in demand for advanced computing devices and AI integrated chips that boost the semiconductor market revenue. And similarly, the smartphones and electronic wearable devices that also drive the semiconductor manufacturing ecosystem. Now, if you look at component-wise, memory devices, virtual reality, which are used for virtual reality and cloud computing, DRAM devices, flash memory chips, real-time embedded processing chips like microprocessors or microcontrollers for IoT applications, and DSP. They are all projected to grow at a rate of 4% till 29. By application, if you see, the major applications for VLSI devices will be in networks and communication segment, work from home culture for the devices which aid that, then automotive application segment, hybrid and electric vehicles, consumer electronics, IoT and automation in automobiles, medical equipment, high definition TVs and laptops, and also all these require packaging and assembly also, so that industry also will have huge market. If you look at a country-wise, North America and Canada, the VLSI market is projected to grow 2.5 times in 29. South American region increase in demand for cloud storage and data centers. European semiconductor market to increase by 30%. And in Asia Pacific, which includes China, Japan, South Korea, Taiwan, Singapore, and India, with the new semiconductor policy, the millions of devices made every year to be consumed in this region as well as to be exported to other regions. Now, just to give a flavor of why VLSI, VLSI started from 1970s when metal oxide semiconductor device was identified to be the building block or the brick of the VLSI industry. And once scaling has come up, the device size have been shrunk to from say 20 micrometer in the 1970s to 4 nanometer in current year, or even 2 nanometer. So this increased chip density has reduced the cost drastically, and the performance also significantly improved in terms of operating speed, energy, as well as area. Now there is a high demand of VLSI professionals because any electronic device has a chip inside. The major job market involves in design, verification, CAD, it's computer-aided design using different tools, whether it is device level design or circuit level or system level design. Then many applications include application specific IC, etc. Conventional research and development, product and product validation engineers. And the major companies are Intel, Global Semiconductors, Taiwan Semiconductor Manufacturing Corporation, which is known as TSMC. Now Tata has today working with the PSMC, Power Semiconductor Manufacturing Corporation, Qualcomm, AMD, Texas Instruments, IBM, Cadence, Synopsys, Siemens, Samsung, Analog Devices, Microchip, Infineon, Freescale Semiconductor, Motorola, Philips Semiconductor, to name a few. These are the major companies. Now Tata Electronics also started, Crompton Greaves. These are the two giants which are starting semiconductor fab in India. Micron also is starting a fab in India, 2 in Gujarat and 1 in Assam. Then microcontroller-based embedded system design, FPGA-based electrical system design, ASIC-based design, VLSI testing and verification. All these are the job openings. If you see any advertisement for VLSI job market, 70 to 80% of the jobs are in VLSI testing and verification. A strong foundation in digital electronics and a working knowledge in VHDL or Verilog, that is any hardware description language, is enough to get a FPGA based firm. Whereas if you want to target an ASIC based R&D job, then in-depth knowledge in device physics, analog and digital circuits, and complete design flow to get into such companies. Now let us come to the topic AI ML in front-end design. So when you say front-end design, you have the specification of a system. Say for example, you develop a signal processing system which will detect some anomalies from that. So you have a system of specification. Once the system of specifications are given, you develop the front-end model. From the front-end model, so the design specifications is converted into an architectural design, and then you actually go for the behavioral level design and the verification. The many AI ML techniques are used in developing this architectural design. Say for example, suppose a particular design involves many number of multipliers, multiplexers, decoders, encoders, etc. So the combinational building blocks in addition to sequential building blocks for a particular or a standard architectural level design, what are the building blocks that are already being used in similar environment. So a machine learning algorithm can identify what are the architectural substituent blocks that are used for implementing a specific design. And now when you give a system of specifications, so specifications include the input variable, the output variable, and their limits. The delay should be so and so, the power dissipation should be so and so, clock frequency should be so and so, the maximum frequency of operation and minimum frequency should be so and so. Like that, there will be a system of specification. So once the specifications are given based on the architecture that are already being developed for previous cases, the ML algorithm or the techniques would be able to come up with an architecture. May not be that optimized, maybe a human interference may be required at the beginning stages, but this AIML, once this AIML techniques are completely learned of these input variable, output variable, and the architecture itself, that this technique can actually come up or evolve with the required hardware design that can be useful for a specific application. So many ML techniques like regression, Mars, hierarchical clustering, CNN, spiking neural network, support vector machine, K-means algorithm, like that. So many algorithms or ML techniques are being used, and all the tools. Now, if you see in Vivado, Vivado is a tool given by Xilinx AMD. Digital design. If you see the latest version of Xilinx, you can see it is ML enabled. That means some ML techniques are already incorporated into the design, so that when we develop a particular system, say for an image processing algorithm, when you want to implement the building blocks that are already there for ML, say for example, if you want to say linear regression, so the models or the matrices which actually implement the linear regression model, if it is already there, we have to just call that as a function and we can use it in our implementation. So even the CAD VLSI tool companies are incorporating AI ML techniques in their design phase, so that we get a most optimized design during the design phase itself. The Synopsys, VCS, MG, QuestaSim, Metagraphics, QuestaSim, Model Sim, Xilinx, Vivado, ISC, Cadence, Virtuoso, all these tools are used for this. Now, if you come to device level, even in device level design, we can use AI/ML techniques. I'll give with an example after this. So, the parametric yield estimation of the circuit and device modeling at the transistor level is the primary focus area at this level. And AI/ML algorithms at different technology nodes facilitates optimization of the device parameters and estimating the yield at a very high computational speed. So what happens is that, suppose we have the device characteristics for a 22 nanometer technology node, and you want to predict what happens to these parameters when the technology node is changed from 22 to 4 nanometer. So we have not got the actual device parameters for 4 nanometer. Okay, we don't have the actual device characteristics for 4 nanometer is not available, but we have for 22 nanometer. Similarly, in addition to 22 nanometer, maybe we have for maybe 18 nanometer, or maybe something less than that. So, but we don't have for 4 nanometer. Now we want to predict for, based on the existing characteristics, we want to predict the device characteristics for 4 nanometer. So this transfer learning approach, using the transfer learning approach of used in ML, or I would say AI ML, you can the model will analyze or study or learn the device characteristics that are available for 22 nanometer and maybe 18 nanometer or maybe 12 nanometer, and then it will predict the device characteristics for 4 nanometer. And then you can actually, after the device characteristics obtained, you can compare with the actual device characteristics at 4 nanometer, and you can come up with the suggestions that, what are the alterations that are required, or whether it perfectly fits the existing results. So that way, AI/ML techniques have huge market in VLSI design space also. So for modeling the IV characteristics of a 12 nanometer gate length, gate all-around transistor technology, a 3-layer neural network with 80 neurons was employed, and performance evaluation of FinFET devices and circuits designed at 7 nanometer and above is becoming challenging. So what is done is like this: a 10 nanometer FinFET database and a 7 nanometer FinFET database. You AI ML algorithms, you study these device characteristics, and a model is trained based on that, and then you apply the device variations that are possible for 3 nanometer FinFET data set, and the device will come up with the actual trained model for 3 nanometer device. So that is what I said: accurate estimation of reliability prior to manufacturing if possible, if we incorporate AI/ML techniques during the device design itself. Similarly, in the gate level design, when you actually write the code and you convert to RTL, that we call as gate level synthesis, the circuit will be synthesized in gate level model. So, say for example, you all know that you create if you want to create an adder, a 64-bit adder, you need full adders and half adders. And if you imagine the circuit of a full adder and a half adder, they are made up of NAND and NOR circuits. Now, if you look at the NAND and NOR individually, they are basically made up of the CMOS transistors. So, if it is a 2-input NAND gate, you will have two PNMOS and two PMOS and two NMOS transistors inside that. Accordingly, you can make a transistor level diagram. So this will be normally done by the tool, that when we develop the code and we simulate and synthesize it, you get an RTL. And in this RTL level design also, we can actually incorporate the AI/ML techniques. Say if you have the PDK means the actual physical design library. That means when the silicon transistor is made or realized onto silicon, what are the device variations, the parameter variations that can come. That model will be incorporated during the schematic simulation itself, so that your schematic simulation result will actually resemble the post-silicon result. So if your post-silicon result and your schematic simulation result are the same, that means your simulation is almost perfect. So in such cases also, for incorporating this advanced model characteristics or device model characteristics onto the design phase or during the design phase, you can use ML techniques. So this PVT is like voltage, temperature, process variation. So which means that if the process technology that you use, you have some certain amount of temperature, vacuum, pressure, etc. during the semiconductor processing, during the manufacturing of say polycrystalline silicon layer or the diffusion layers or ion implantation layers, etc., etc. So this process, there can be variation when you go across the wafer from one end to the other. Similarly, if you do one process in a particular run and the next process in a subsequent run, there can be variation from one run to the next run also. So what are the process variations that normally can come in a manufacturing environment? And similarly, what can be the voltage variation? Suppose you imagine that you have designed the threshold voltage for exactly say 0.45 volt, and when you actually manufacture and you measure the characteristics, it is something like 0.452 or 0.448 or 0.447, something like that. So that means there is a difference in the threshold voltage that has come up due to some process variation or voltage variation that has come. Similarly, when you have the temperature variation, what is the change in the, because semiconductor being a temperature dependent a region or device, as the temperature increases, the conductivity, electron hole pair generation, all that will change, and that will create a change in the conductivity, resistance properties, etc., etc., and that can also differ from the expected characteristics. So this PVT variation can be modeled. So if you analyze the PVT variation at the one technology node And if you want to predict what could be the PVT variation at a larger, I mean a lower technology node, in the sense 22 to 4 nanometer like that, you can actually emulate that behavior at a lower technology node and predict what would actually happen at 4 nanometer. So that is the meaning of this PVT aware circuits. And you have the input variables, output variables, normalize the input data, etc. You train the device and you get the trained ML model will have the circuit parameter prediction. So this particular circuit will predict what would be the model variations with respect to process, temperature and voltage variations. And so that these changes, the limit, you see the maximum and the limit, minimum limit of these parameters will be already identified, and then any particular change in the process need to be done for making the parameter within the limit, or can we go ahead with the production itself, whether all the parameters are normal, that will be identified then. Similarly, for the back-end design, that is the synthesis level design, there also AI/ML techniques are used. Say for a netlist DFT insertion. So DFT is like design for testability. For inserting design for testability, say for example, you have inserted design for testability for one specific design. And so what it does is it introduces stuck at 0 and stuck at 1 faults within the circuit, and it identifies whether any of these stuck at 0 or stuck at 1 faults are getting propagated to the output. And if it is getting propagated to the output and that propagation creates an error, then that that particular fault is detectable or observable at the output. So now you need to identify a scanned cell insertion for the different interconnecting lines within the complex circuit, such that all the nodes are becoming like observable and controllable. So if the controllability and observability of all the nodes are can be defined by specific numbers, then we say that that design is very good design. So for incorporating, because when it is a complex circuit, incorporating the observability and controllability aspects for every node is a very, very tedious process. And even for that, we can use ML techniques or AI/ML techniques to insert the required scan chains or the DFT capability within a new design or within an unknown design. For that also, we can use AI/ML techniques. So these are the techniques that are used, and the code and the tools that are given by these vendors for this design. Now coming to physical design. Physical design involves identification of from the schematic, it converts into a layout, and during the layout simulation, the post-layout simulation results will be considered or will be compared with the schematic level simulation, and you can see whether the when the device is actually getting fabricated, whether the expected result is coming up. Okay, so during this phase also we have multiple levels of design. We can say floor planning, that means which IC or which gate should sit where. That is the meaning of floor planning. And placement. Then routing means interconnecting them. So interconnecting multiple input output layers, intermediate layers, etc. Then if it is a synchronous circuit, you will have clock everywhere. So the clock also need to be distributed. Normally what is done is a separate interconnecting layer will be used for distribution of the clock tree, and then through the wires this interconnection with multiple layers will be taken place. So then that clock tree synthesis and timing analysis, layout verification, and finally signing off with a GDS file. So that is these are the steps in a physical design. So then AI/ML techniques are used at, say for example, just to give you a feel of this floor planning. Suppose you have the placement and routing architecture of a particular complex design you already have. So you give this as an image processing problem to the model, and the model identifies that for a system of input and output specification and timing constraint, and for a system of constituent architecture, this is the way the blocks are identified within the architecture. Now, if you come up with a new architecture, the system will be able to predict what should be the way these items need to be, I mean, these sub-modules need to be distributed or planned in that. So we can identify that. So, which means in the training, I mean, the placement and the routing, we can use that. Then clock tree synthesis and timing analysis. Say, for example, assume you have, you are calculating 1024 point or 4096 point FFT. So within that FFT, you will have many number of multipliers and adders. Now, suppose you want to implement another system in which you want to use a transformation or convolution. So when you implement the convolution, you have matrix multiplication. So for that matrix multiplication also, the multipliers that are used for the FFT can be used. So now, based on the analysis of the FFT data, which was your previous design, your model has some information about what is the requirement of power, what is the requirement of speed, area, etc. for the multipliers. Now, for when you use it for an image processing application, there when you analyze how many when you means the model analyzes how many multipliers are required, it will come up with a strategy of this is how this should be placed and routed, and this is how the clocks need to be distributed so that minimal the parasitic capacitance will come and the clock skew, jitter, etc. can be minimized if you have a proper distribution of the clock. So in all these cases, we can use, I mean, people use AIML techniques for the design specification. And coming to the fabrication, even in the fabrication level also, we can actually use AIML techniques. So for example, for lithography, when you transfer the pattern, you have to design a mask. So for that design of the particular mask, if already the model is trained with the design of the mask for n number of device structures, then this AIML technique can actually predict a proper mask design which can be used. So, and where should be the marking given, the alignment process can be done faster if the particular design has the marking scheme different from what was already there. Like that, it can come up with the different proposals for making it a better design. Similarly, during the packaging testing, the chip final test and post-silicon validation, that means after the chip is manufactured and packaged, the testing result of that. All these different phases, different AIML techniques, I've written in here, it is available, all the different techniques, clustering, semi-supervised learning, pattern matching, ensemble classifier, all these techniques are used at different parts of the design or different phases of the design, and it is also used by the industries also, means cadence, synopsis. These industries also actually use these techniques at different design phases. Just to give you an example, we had developed one digital system and say maybe one division module. So that module we simulated in Vivado, we simulated in Xilinx ISC, we simulated in CADE 3 versions of Cadence software and Genus tool. And based on the version of the Cadence, the power and the delay analysis was different in each. So now when we assume that, this is a standard semiconductor tool or a simulation platform, it should ideally, we ideally expect equal result for all the versions, but we find that based on the version of the software, the actual values were different. Why it has come is that the optimization techniques that they have used in different models are different, or different versions are different. Based on that, our results were also coming to be different. So that is how we try to analyze that, how this change can be nullified. Now, if you see this is just an overview of all the AI techniques that are used specifically for VLSI design. Supervised, unsupervised, reinforced learning, and deep learning techniques are used. So this is the summary of whatever I have told in circuit simulation level, device level, gate level, circuit level, RTL level, post layout level. We can use AI/ML techniques. In architecture level, memory system design, the systolic arrays, everywhere people have used this. All these are papers demonstrated in different areas of VLSI, wherever people have used AI/ML techniques. Development of system on chip, and in physical design for partitioning, flooring placement, clock tree, and routing it has been used. And in the manufacturing, lithography for analysis of yield and reliability, this AI/ML techniques have been used. And in the testing phase for functional verification, fault coverage, and scan change diagnosis or scan change insertion, all these phases, AI/ML techniques are used. Yeah, so this is almost same as, yeah. So now if we see individually, for chip floor planning, people use reinforcement learning, post P&R stack prediction, machine learning, and methodology for SRAMs, routing, congestion evaluation, regression methods are used, data path logic extraction, SVM and CNN methods are used, chip fit placement optimization, RL reinforcement learning approach for faster placements. So placement and routing, you have deep learning as well as CNN models. Like that, if you see whether it is flooring and placement and routing or it is clock tree synthesis, you have n number of AI/ML techniques that can be used for better design. Now, if you come to AI for manufacturing, the lithography, which transforms the data, layout data into geometric patterns, and during the design phase of mask synthesis and verification challenges, we have used, people have used AI/ML techniques. Now, what is done is, during the training phase, certain patterns from based on the coordinators are being considered or are being taken by the model, and during the testing phase, these the parameters that are required or produced by the model will be decided or will be developed by the system. Now, AI/ML is also used in functional verification for VLSI testing. It has been used in random test pattern generation, KNN for test pattern selection, Bayesian network for test pattern prediction, machine learning for functional verification, explainable ML for test point insertion, and pattern identification and reorder. So all these all these cases are applicable for, all these different machine learning techniques are applicable in the case of VLSI testing, testing and verification phase also. So now, if you look at the design phase that are coming up in future, it only software hardware co-design will be able to sustain in the VLSI industry. You cannot go only with the software, you cannot go only with the hardware. Both software and hardware co-design the chip that are to be manufactured or exported will have all these techniques involved inside this. That means the software and hardware will be co-designed. Software hardware co-design means during the design phase itself, the software capabilities are incorporated into the chip that are designed, so that it is very seamless integration between the software and the hardware are possible. One example I would say, we all would have heard about in-memory computing. In-memory computing is one in which the data to be processed are actually saved in a crossbar array, and the data will be taken from the crossbar array, and after every computation the data can be stored back into the array itself, so that we can have like every time the read and the write cycle are getting immensely uh, benefited by this architecture, so that we don't have to, it is not the conventional von Neumann architecture where the data has to be taken from inside somewhere, I mean the memory cell. But here the data is available in a crossbar array, which can be directly linked with the processor, so that that read-write cycle problem can be nullified. So that is what the new era is about. It is actually the accelerator co-design. There are accelerators which work on softwares, but there are, the main focus should be to work on hardware-based accelerators for VLSI people or semiconductor people, so that, these accelerators will have huge impact in the design phase or design ecosystem. So hardware accelerators are there which can achieve very high performance, lower die area, power, and cost, and it should evolve from CPUs to specialized ASICs. So if you look at Intel, all the Intel processors are generic purpose processor which can be used for multiple applications. Now the time has come that they also are planning to develop ASICs like GPUs. GPU is NVIDIA product like graphical processing unit, which are mainly manufactured by NVIDIA, and they have already incorporated AI/ML techniques into their processor, and they can claim like this is the first processor, from this AI/ML background. And then accelerated design insights, code design across the entire ecosystem, focus on networking, scheduling, scaling, visualization, etc. Application level opportunities in expanding capabilities, video accelerator enabling live streaming, cloud gaming, then software defined hardware, control and automation, and future prospects. So these are the points that are to be taken from new era of accelerators and co-design is such that navigating challenges and opportunities, because they the people in the country have identified that unless you go forward for a design that are manufacturable, okay, if you do some design and if that design is not manufacturable, absolutely there is no point. So if you make a design that is manufacturable, that means you are actually making up a design which can go along with the real hardware. So the uncomfortably exciting future of VLSI industry is that unless we are ready to work with the software hardware co-design approach, it may not be possible to sustain. Yeah. Now the future hardware, this was given by this Dr. P. Ranganathan. His talk in 2023 IIITT Symposium on VLSI technology and circuits held in Japan. He has presented this paper, the future hardware, AI-driven, software-defined, uncomfortably exciting. This is actually the title of the paper. And P. Ranganathan, his professor, has given about this paper, and he has mentioned that there are a lot of opportunities and challenges for computing from the AI-driven future, but the recent pivot to software-defined hardware across accelerators and hardware-software co-design, so that is very important. So the hardware alone cannot sustain, software alone also cannot sustain. So you can have a comparison or a combined version of both together, so that it is like a software defined hardware design. So even though as VLSI specialist, it may not be possible for us to go with that particular design, but without that there is no future. That is what he says. So it is an uncomfortable exciting future for the semiconductor experts who may be less willing to change or shift their focus onto developing software hardware co-design. Now, for the last 15-20 minutes, let me just give a brief of the work in neuromorphics that we do at the IIITDM Kancheepuram, my institute. So, the neuromorphic circuits that we work basically are involving neurons, synapses, and neural networks. But this particular neural network is different from the conventional neural network. Basically, the difference is that this is a spiking neuron. This is based on a spiking neuron. Spiking neuron mimics the functionality of the brain. It actually, what it does is it accumulates the charge, and whenever the accumulated charge is more than the threshold, it gives a spike. So it is originated from 4 pioneers: Max Delbruck in 1969, Paul Muller in 1980, Eric Vitos in 1984, and Carl Maid in 1993. So these are the pioneers of this field, and what shocked them was that brain is around 1.5 kg and 2% of the body weight, but it consumes only 20 watts of power. Only 20% of the energy of the whole body is being spent for functioning of the brain. So this is what the neuroscientists were amazed at, that how that human brain can work at a very low this speed and weight, and then power. So the human brain has around 100 billion neurons. During the brain development, 250,000 neurons are added every minute, and by the age of 2 years, the brain is about 80% of the adult size. And from age of 20, the brain starts losing 1 neuron per second due to aging. This is the diagram of a neuron. The neuron has cell, membrane, the soma, the cell body, and the nucleus. In addition to that, it has dendrites, which acts as the legs, so which will communicate with the other neurons. And at the tip, there is something known as axon that is converted to, and that is connected to some axon terminals. So how this neuron actually communicates is that when the sodium, potassium, magnesium concentrations are different inside this, there are receptors and a path for which they can, they will open and close. Based on that, there will be ion movement within and across the cell membrane, and that is how they create a potential. So the action potential flow will be like from soma, it comes to axon, and then from synapse and the dendrites to the next cell. So there are neurons which are presynaptic and postsynaptic neurons. Presynaptic neuron is one which will receive a spike before the post has occurred, whereas postsynaptic spike is that it will receive a spike at the post after the pre has arrived. This is the shape of the action potential characteristics. We can see that this is somewhere like the resting potential. So it rests at this voltage, and then it accumulates charge, and when that accumulation of charge is greater than certain threshold, it fires. And immediately as it fires, this voltage which are accumulated in the capacitor will be completely discharged, and again it will be waiting for the next spike to accumulate charge and trouble. Yeah, so now the ion channels, as I mentioned, are Na plus, K plus, Ca2 plus, Cl minus. Membrane potentials are difference in electrical potential between the interior of a neuron and the surrounding extracellular cell medium. And there are inhibitory and excitatory neurons, which means that whichever neurons which give spike even under a stimulus are known as excitatory, and which neurons which do not spike even if whatever you do, such neurons are known as inhibitory. They can be dynamic in nature also. Now, there are different neuroscientists who have proposed models for this digital neurons. One such professor is Professor Isikiewicz from Cornell University, USA. He has modeled this neuron as its neuron. So the relation between the membrane potential V and the recovery variable U and the input current, these relationship are like non-linear here, means they follow square law. So these devices, when what we do is we model this equation into digital domain and we implement them in digital domain, then we will be able to generate the spikes. So these are some examples of the spikes that we have generated. And then we had, also worked on integrate and fire neuron model. There the equation is an almost linear equation. It is not non-linear. So there also we have generated the different types of potential, the stimulus, tonic spiking, class 1 excitable integrator, etc. And then we have also come up with some neuron model which will enhance the property of the neuron. So we added to implement a neuron model which gives like this: C d by dt equal to Im plus I, because that will give the reset condition, etc. And the parameters are given here like membrane potential, etc. And we were able to reproduce the same result like whatever was obtained before. And this is the circuit that was modeled as an analog neuron model. Here there are two inverters, and this discharging phenomena through these transistors are actually controlling the control voltage. Yeah, so these are some examples of the spiking neurons. We can see that in the spike interval is almost constant, in this case for this spiking neuron. And there are different learning methodology for the SNN to be implemented, and these learning methodologies are known as 5 timing dependent plasticity, pair based and triplet based. So there are a system of equations which need to be implemented, and then if you follow Poisson's, so if you follow, 1 second, I need to just take a call. In a lecture, I will call you back. In a lecture, I'll call you back. Yeah. So these equations we need to model in digital domain, and because it contains exponential functions, implementing exponential function will be tedious or will be computationally intensive. So we have used some approximation for the exponential function and found that with the error with the minimum, we were able to reduce the exponential quantity, and the same exponential function was used in an implementation of the STDP rule, and we were able to reproduce the characteristics there also, and it was giving better result with respect to this. Another work what we have done was a reusable spiking neural network architecture, in which a neural network was made, a spiking neural network was made like this, where STDP, memory and Isikiewicz neuron was part of every neuron, that is the synapse and the memory and the learning methodology. So then we applied, this is the detailed view of what is this, and then we applied different inputs and trained this circuit to be applied in 2 different applications. One was just identification whenever a robotic arm movement was happening, and another one was like a pattern or character recognition. And these two, both the applications, it was successfully implemented, and a comparison with the existing results also. Then we worked on another problem known as heart rate classification using TSTDP and BCM characteristics this is the ECG signal. Maybe you would be knowing this. So P, Q, R, S, T are the waves that are there in the ECG. So if you can see here, the end of P to beginning of Q, and the end of S to beginning of T, and from end of T to beginning of P, these are defined as segments, whereas interval will consider the wave as well as the segment together. So there is, for a healthy heart, there are specific timing durations for each of these segments and intervals. And if any of these, segments or intervals, as well as any of these beats and the sequence or the polarity are all getting changed, then based on that, the health of the heart can be identified. So that was the intention behind. We used the BCM learning rule to identify the heart rate, whether it is normal, abnormal, etc. For that, we implemented the pair-based and the triplet-based STDP characteristics. Pair-based, which only finds or compare a pre and post-synaptic thing, whereas here in TSTDP we use a triplex, means either 2 pre and 1 post, or 2 post and 1 pre, were always taken together. And these are the equations that are used for TSTDP. The advantage of TSTDP circuit is that when we implement that, we can actually make use of BCM characteristics. BCM characteristics is universally accepted by the neuroscientists that it is a very good classification algorithm. So we implemented that, and we were able to determine whether the heart rate is normal or abnormal, like that. So this is the result, the actual heartbeat pattern. So we were taken, like, if the heartbeat is between 60 to 100, it was taken to be normal. Less than 60 and more than 100 was taken to be abnormal. So that we were able to obtain that. And these are the comparison with existing result. In addition to this digital implementation, we have also done analog neuron implementation. So these are the different circuits and some of the power saving techniques like force tracking method, etc. we have used in these circuits to reduce the power. And accordingly, we have obtained the spiking characteristics. We have analyzed the different properties of the neurons, such that spike frequency adaptation and different types of spiking patterns. And then we, based on the original model proposed by Gressner, this is Professor Gressner from EPFL Switzerland. He only proposed this ADEX model. And from there, we have come up with the revised version by modifying the current mirror comparator, and we were getting better results in terms of okay. Yeah, so these are the results, energies per spike and percentage decrease, etc. we had compared. And the same neuron we have used as an encoder, because the neuron, the spikes generated by the neuron is a replica of the input magnitude. We thought that, we can use it as an encoder. So for that, this was the conventional circuit which we modified this way. And we got a much better result. So this is the encoded option of a sinusoidal signal. And from what we did was, we took these spikes and given to a mathematical system for the reconstruction. We have developed that, and that reconstruction system developed the error between the two, which was found to be very, very low. We got an signal to error ratio of 60.84 dB and an effective number of bits of 9 bits. And the comparison with the different conditions were done, and we got very good results. Similarly, we have also implemented the PSTDP and TSTDP circuits, analog circuits, which already existing. We have done some modification by implementing the transmission gate based approach for window generation, that was eliminating the delays introduced in the circuit. and we were able to demonstrate that. And the same PHTDP circuit was able to show the BCM characteristics also when the pre and the post spiking rate was following the Poisson spike ratio. And then we also used memristor because memristor is the fourth element which follows the passivity condition, and the memristor being a memory element can be used for implementing this learning methodologies. So we have used a memristor also in that, but this result is not yet communicated. We will do so in near future. So these are the memristor characteristics that we have got. We have implemented a time division multiplexing scheme to talk between different stages of the neuron circuit so that we actually reproduce the long-term potentiation and long-term depression characteristics of the neurons and the synapses. This is the final circuit, and we have got the TSTDP implementation also. Yeah, so these are the students who have worked with me. Satyajodi currently in NVIDIA, Pavan in MathWorks, Madhuvandi, she is doing PhD at ISC Bangalore, Amrita Manoharan, she is at NXP Semiconductors, and these are my PhD scholars and project staff or JRF who are working with me. And these are some of the papers, only published papers have included here, and these are references. Thank you very much for your patient listening. This was like a one-sided affair. So if you have any questions, please.
Thank you for your talk, ma'am. Ma'am, I'll propose a question from the audience, like one of them had asked me. In the field of neuromorphic circuits, what has been the most interesting or like unexpected thing you have encountered till now?
Okay. Unexpected in the good sense or bad sense, I am not very clear. Unexpected means when you say that we have got some good result. If you ask me, you see, mimicking the human brain, For example, you see, if you can emulate a photo detector. You see, you may know the photo detector. Photo detector is a circuit which absorbs light and converts into electricity or current. Now, if you can create photodiodes which can identify different colors, and you imagine that these are actually modeled as a panel. Okay, now somebody whose retina is damaged, but brain is functioning properly, assume. Okay, we can replace with this set of photo detectors for the retina, and then the brain, the particular part, the region of the brain can be stimulated with the signal that are coming from these photo detectors. Okay, and then the person can restore his eyesight. So like that, you have tremendous opportunities are available here. When you actually go through that, we get like a lot of ideas like, can this be done, can that be done, like that. So there are many positives. So if you look at the negatives, the spiking neural network is not a mature technology. It is still in the research phase. So if you look at conventional neural network and deep neural networks, that there are, every day we are getting new models. New models means models capable of implementing very complex functionalities. So, if you want to implement like any type of detection and classification, say for example, you take an MRI image and you say that whether this is cancerous or non-cancerous, whether a particular lesion is there or not, etc. The model itself will predict that whether these cases are there or not, and based on the prediction, these cases can be referred to a clinician or a doctor, and doctor can come up with a decision. So like that we can use, but spiking neural network is not that mature enough. So it has to come up People have to work more on that to incorporate more learning methodologies onto the network, and then only it can become a mature thing. So that is the shortcoming as of now in this area that I am working, the learning methodologies now. But today we saw a paper, just today we saw a paper on reinforced learning implemented on SMN. So like that, papers are coming up. So, yeah. I don't know whether I answered correctly, whether this is what you meant. Yeah.
Yes, ma'am, I definitely meant it in a positive sense. I extend our heartfelt gratitude to you for making this seminar possible and venturing us into the field of semiconductors and your specific areas of research. We thank you for taking time out of your busy schedule at such a short notice to enlighten us with your words, ma'am.
Thank you. Thank you very much.